Hello everyone, my name is Zewei Li. I'm from University of Cambridge. I'm a PhD student in the optoelectronics group in physics. My supervisor is Richard Friend and Robert Hoy. Thanks for MRS. It is very nice to have this opportunity to share with you our work in this meeting. Our work is about bandgap lowering in mixed alloys of cesium silver, antimony bismuth bromide double perovskite thin films. This project is part of the work in searching for light-free alternatives, and we focus on the double perovskite structure. A perovskite has a crystal structure as shown. It has a mesoammonium or cesium ion surrounded by 8 octahedrons. In each of the octahedra, there is a light ion in the center, surrounded by 6 halide ions. To become a double perovskite, the cesium ion and the bromine ion do not change. What changes is the octahedral center. It is now occupied by 2 different ions alternatively. In our case, it is silver and bismuth. The good news is this material is light-free and has relatively long carrier lifetime, but its bandgap is indirect and large. People are finding ways to reduce its bandgap. For example, in this paper, they are alloying antimony to bismuth in a powder form and found a relatively large bandgap reduction. However, they found an alloying limit of 37.5% for antimony. We are inspired by this alloying method to reduce bandgap. 3 questions arose in our minds. Question 1 is, can we do it in thin film form? Because to apply it in devices such as photovoltaics, it needs a compact thin film. And we also want to see what extent of reduction can be achieved in thin films. Question 2 is, we want to try if we can achieve the full alloying range. If we could, how will the bandgap change, and why? Now let's turn to our work. We achieved the full alloying range in thin films. Films are about 200 nanometers thick. We can see the films with 90% to 50% antimony show deeper color, although the color variation is small. Then we did some characterization. Firstly, we characterized with RBS and saw that the stoichiometry ratio in our thin film are the same as their precursor solution, with little deviation within the error range. Next, we checked the crystal structure with XRD and found no phase segregation or impurity phase. We observed larger fluid self-maximum on alloying of antimony and attribute this to higher disorder and grain size effect. According to calculation, only the bismuth perovskite grain size should be larger if it is due to grain size effect. This is confirmed by the SEM plots. All the films containing antimony display small grain size, and only bismuth one has large grain size. We then use standard UV transmittance and reflectance measurement and PDS to characterize absorption, and use top plot to determine its bandgap. Interestingly, we found that the antimony-rich mixed alloys have smaller bandgap than either pure material. It doesn't obey the conventional Wiggers law, where we will have a linear bandgap behavior. Why do we have such a large buoyant here? This is a key question in this project, and we dig further by calculation. We calculated the band alignment from a heterojunction structure. We found antimony double perovskite has both higher CBM and VBM than bismuth double perovskite. So why is antimony double perovskite shift up in energy? For the CBM, the third ionization energy gives a better estimate for the ion-occupied p orbitals, which constitute part of the CBM. Antimony has a smaller third ionization energy, so it is less negative and in a higher energy state than bismuth. For the VBM, bismuth has large atomic number. Due to the relativistic effect, its 6s orbital contracts. So bismuth 6s orbital is in lower energy state than antimony. Antimony 5s orbital is closer to the bromine 4p orbital, leading to stronger interaction and push the VBM up. So antimony double perovskite also has higher VBM. We are now clear with the band alignment. We will see how this is related to the large buoying in the bandgap. The band gap of an alloy usually comprises two parts, a linear part and a bowing part. The bowing parameter is usually positive, so the final mixed alloy bends downwards. From literature, there are three reasons for the bowing phenomenon. Chemical effect, which is due to the difference in electronegatividity, local size mismatch effect, and changes in the lattice parameter. The last two factors are structural effects because the origin is atomic size mismatch. In our system, the two lattice constants are very similar, and the band gap deformation potential calculated is very small compared to the large experimentally observed bowing. Therefore, these two structural effects are ruled out. We propose that the large bowing is from the chemical effect. Chemical effect is a nonlinear mixing of atomic orbitals due to the electronegatividity difference. For example, if we have two materials with such band alignment, we can imagine two extreme conditions. In the first condition, these two materials are quite chemically similar. The energy orbitals of the alloys will mix nearly perfectly. This will lead to the linear variation of the band gap. In the other extreme condition, if these two materials are so chemically distinct, the bands do not mix at all. What would happen is like the CBM and VBM of material A is inserted into the gap region of material B. So the band gap will be the same as material A. The reality will be a compromise between these two extreme conditions, so we will have a bowing deviation from the linear trend. This situation is for such band alignment. It is called type 1 alignment. We can also have type 2 alignment, which is similar to our case. The linear condition is the same. However, in the other pole, when the two materials are quite chemically different, the orbitals do not mix. The mixed alloy will have CBM of material B and VBM of material A as its band edge. It will have a band gap equal to E minimum. Again, the reality is a compromise. It can be like this curve. We need to know that this type 2 alignment can also have this small bowing curve as long as the two materials are similar. It is just only in type 2 alignment the mixed alloy can have band gap smaller than either pure material. This is exactly our case. In the mixed alloy, the VBM wave function preferentially allocate to the antimony site, and the CBM wave function like to allocate to the basement site. So we have a smaller band gap in the mixed alloy. We did some calculation and XPS-UPS measurement on the mixed alloys. The calculation results validate our proposal. For this mixed alloy, the VBM has more SBS characters and the CBM has more bismuth B characters. In the XPS-UPS results, this preferential allocation of the wave function is more obvious for the CBM, which may be due to the spin-orbit coupling introduced by bismuth. In conclusion, I find this figure is a good representation of our work. We successfully synthesized the full alloy range of antimony bismuth double perovskites. The mixed alloys have the smallest band gap. We propose it is due to type 2 band alignment and the strong nonlinear mixing of the electronic states. Although it is under debate whether double perovskites are promising for photovoltaics, its properties are suitable for photocatalysts and hard radiation detectors. The bandgap lowering mechanism can also shed light on better understanding of the perovskite band structure. I would like to thank Cambridge Trust and China Scholarship Council for providing my funding, and a huge thanks for all our collaborators, especially Sean, our calculation collaborator, and Richard Friend and Robert Hoye for supervising this project. Thanks everyone for listening. I'm happy to answer any questions. Here's my email address. Welcome to contact me for further discussion. Below is a published version of this work. You can find it online. Thanks again for all your time. Hope to see you next time. Bye-bye.